Bismillah ar-Rahman ar-Rahim. Allahumma salli ala Muhammad wa ali Muhammad. All right, I'd like to welcome you to my video devoted to the 5x5 wifq, or so-called magic square as they're called in English. This video has been a long time in coming. I've been really busy, so I wasn't able to actually film it and put together the materials for it. I was busy with various projects. I'm working on a project with a colleague who's abroad. I'm working on some manuscripts and so forth. And I also have been working on a course which I'm going to be teaching, which is called the Quintessence of Wisdom. I've advertised it on my Facebook page, so please do check it out there. And I also have a couple of other announcements. I receive various questions, on my YouTube channel, so I'm going to indirectly address one of those with reference to certain books, because I made a video about some what did I call it? I'll call it reading lists. So I want to add some books to that, and indirectly address one of the questions which was posted on another video. And before I do that, I do have another request or announcement, and that is that there's about 49% of the people have actually subscribed. Sorry, no, I think not 49. It's 41% of people have subscribed, and then about 59 have not. So I would just request everyone, to subscribe and to also click on the notification bell so that you can be informed when new videos are uploaded. Okay, so I had mentioned certain books. So somebody had asked me on another video, in reference to another video, about the difference between the Western system of astrology and the so-called Hindu or Indic or Vedic astrology, which is called Jyotish. And they thought that maybe there was some differences between Western and that had to do with past cyclical ages, or what's called a yuga in Sanskrit. And that's not really true. So I don't really think that's true. So I would recommend people who are interested in Vedic astrology. This is the most accessible book I've found on it. It's called Vedic Astrology by Ronnie Gale Dreyer. It's very readable. And there are a lot of worked examples, so I don't actually do this kind of astrology because I'm not, it requires a lot of experience naturally, but this will give you an overview, and if you do want to work on that, you can get started, and hopefully you can find a teacher, because these kind of things really require a teacher. The real difference is that the Jyotish or Vedic astrology takes into account what's called the precession of the equinoxes. And since it takes into account the precession, it differs from Western astrology. So they have the two zodiacs. There's the sidereal zodiac and the tropical zodiac. And the Vedic astrology uses the so-called sidereal zodiac, which takes into account this shifting or wobbling of the Earth's axis, which will change the position of the constellations. And so if you want to adjust, there's an adjustment factor called the Ayanamsha, which is about 23 degrees, and you add that forward and you'll be fine. So that's one book I would like to recommend. Also, related to astrology, there's this very nice book called Cosmology in Antiquity by M.R. Wright, which has also a very interesting discussion of astrology, and actually walks you through how to put together a chart using the Western system. I mentioned about alchemy last time in that reading list. So these are some other recent books I came across on alchemy, which I found very interesting. There's one called Alchemy, the Great Work by Cherry Gilchrist. This is very readable and very inexpensive. Then there's Gene Cooper's book on Chinese alchemy. So this is also quite useful. And I was visiting some used bookstores recently, and I came across some real classics. Very nice book called The Tao Magic, The Chinese Art of the Occult. This is a really nice book with beautiful pictures in it. And some of you might know, I lived in Egypt for many, many years. I spent a lot of time in that country, and I was very sort of interested in Egyptology. And there's a famous series of books on the Egyptian pyramids and the Mexican pyramids by Peter Tompkins. And Peter Tompkins also has a book on the magic of obelisks. It's a fantastic, very interesting book full of all sorts of bizarre information, but it's hard to find. And recently, a couple of weekends ago, I found it in a used bookstore, and I was really quite happy. Last but not least, is this book. This is very expensive, but if you can find it, it's called The Dragon in Medieval East Christian and Islamic Art. Absolutely fascinating work if you are interested in mythological beasts. Excellent. Let's now get to the 5x5 magic square. In this video, because the 5x5 is much larger and there's more possibilities for making errors, I've already written out all of the material on this large brown sheet of paper, and I'm going to walk you through it, and I'm going to explain everything. Now, to refresh everyone's memory, I think I said in an earlier video that the 3x3, the 4x4, and the 5x5 magic squares, or awfaq as they're called in Arabic, are absolutely fundamental. And among the reasons for this is that all of the larger squares, or almost all of the larger squares, are in some way or another composed of these smaller 3x3s or 4x4s or 5x5s or combinations of them. So for example, if we go to the 6x6, the 6x6 can be seen as a collection of four 3x3s, two on a side. In other words, if you have a 6x6, then there will be 36 cells in it. And so you can imagine a 3x3, a 3x3, and another 3x3, and another 3x3 all put together. Now, if you go to 7, that no longer holds. A 7x7 is all by itself. 7 is a prime number, so it's not going to break down into these. Well, what about 8x8? So if it's an 8x8, then 8 squared is 64. That means there's 64 cells in that array. And that means that on each side, there's two 4x4s, meaning there are four 4x4s in an 8x8. How about a 9x9? Well, yeah, that's an odd number. It's not prime, so it can be broken down into threes. So a 9x9 will have how many cells? It'll have 81, or 3 3x3s on a side, or 9 3x3s in all. So you see how that works. If you've got a prime number like 11, it's not going to happen. 13, you're not going to be able to decompose it. Let's say you had a 10x10. Well, that's just 4 5x5s. And the mother of all magic squares is the 100x100, which reputedly goes back to Aristotle, who taught it to his teacher, because he was the teacher. He taught it to his famous disciple, Alexander the Great. That's what's written in certain manuscripts. In fact, there's a very interesting occult manuscript in the manuscript collection of Princeton University Library. And in fact, you can find it online. You can download it if you can read Arabic. It's free. And tells you how to construct the 100x100, or what's called al-wifqul mi'ani in Arabic. And since you've got 100x100, so how many squares do you have in it? Well, that's 100 squared. So if you don't know what 100 squared is, you can just think of 100 as 10 squared. And then you square 10 squared, which means you'll get 10 to the fourth, and 10 to the fourth is 10,000. So you have 10,000 cells in that. And so you can think of that as what? You could think of it as 5. Yeah, you could think of it as 25x5s. Or 25 4x4s. So in other words, you would have 25 by 5s on a side, or you would have 25 4x4s on a side, and you would still get 100x100. So that's some of the background mathematically of why that's important. Okay, also with the 5x5, I'm not aware of as we have with the 3x3 and the 4x4, these different ways of filling it so that you have one corresponding to each of the four elements, like earth, air, water, and fire. I'm only aware, and this is the extent of my knowledge, and I'm happy to, say that in public. I don't pretend to know things that I don't know. So this is the only form of the 5x5 that I am aware of. So if we come here, I'm just going to point, I'm using this wakizashi from the Hyoho Niten Ichiryu school of swordsmanship founded by Miyamoto Musashi. It's far more elegant as a pointer than just a twig. So this is the 5x5 magic square. And you see the 1 begins in the upper right hand corner. And again, the knight's move is paramount. So the knight's move from chess, you go to the left and you come down, you've got your 2. Go to the left and come down and you have the 3. Then you've got to double back this way and you've got your 4. Then knight's move again, you've got 5. Then you can't go anywhere, so you put the 6 up here. And you've run out, so now you come all the way up and you go to 7. Okay, so then you come back, you've got 8. Knight's move down 9. And then 10, 11, 12, 13, 14, 15, 16, 17. And you see 18 is here. 19, 20, 21, 22, 23, 24, and then 25 will be the last one. Now, please recall the mathematics involved here. There was a general formula. So if we come here, this is the general formula. If you remember, the number S representing the magic constant, as it's called, is equal to A times N plus beta times n over 2 times the quantity n squared minus 1, where of course n is greater than or equal to 3 because you can't have a smaller than the 3x3 square. Now you need to remember that what these variables mean. So S is the actual value. So in the case of a 3x3, S would be 15. And I'll tell you that in the case of the 5x5, it's going to be 65, but I'm going to show you why. So A is the minimum number. So when we have other sorts of values that we want to encode, we need to know where we start. And beta is the skip constant, which is, in our case, it's going to be 1, or the interval, the increment will be 1. And then n, again, is just the number, the order of the square. And so here we are using this formula to determine what will happen with the 5x5. So n will equal 5. And we're counting by 1s. 1, 2, 3. We're not counting by 2s or anything. So the beta is going to be equal to 1. Now, if you plug all that back into the equation, then S is going to equal 5a, because n is 5. Remember, beta is 1, so we write a 1 here. So it's plus 1 times 5 over 2 times 5 squared minus 1. Now, 5 squared is going to be 25. Everything else is the same here. 25 minus 1 is 24. And then you see that 24 is divisible. You have a 2 here, so it's divisible. You divide it by 2, you get 12. That'll be 1. 12 times 5 is 60, and you'll have 5a plus 60. Now, when you have 5a plus 60, you have to remember then that this 60 will actually be what's called the subtraction factor. So let's say you have some other number that you want to encode. In other words, you need to know what the minimum value will be, where you start. So let's say you wanted to encode 125. That means that S has to equal 125. So the formula here for A is going to be S minus 60. And then you'll have this divided by 5. That will be what A will equal. So you would have to see, okay, well, let's see. Let's say if we have 125 minus 60 divided by 5. That will be equal to our A. So that's what we always do. So in this case, it would be 125 minus 60. What's that going to be? Anybody know? Well, what's 120 minus 60? It'll be 60. So it's going to be 65, isn't it? Then 65 divided by 5. What is that? Well, it's going to be 13. So you would start at 13, and there's no remainder. Let's check. Is that right? 13 times 5. Yep, it's correct. So that's just an example. We'll work out some proper examples. So in this case, then, if A equals 1, because we're starting here with the minimum value of 1. So if A equals 1, we get the value of S is equal to 5 times 1 plus 60. And that obviously will be 65. which means that in this magic square, all rows, columns, and diagonals of the 5 by 5 must sum to 65. So everything here, all the vertical columns have to be 65, all of the horizontal rows, and the 2 diagonals. Now, unlike in the other videos, there's just too much arithmetic calculation involved. I don't want to take time on that. If we focus here on this square, you can make a one for yourself using some graph paper. And here I would advise you to pause the video and confirm that every horizontal row and every vertical column and each diagonal sums to 65. So pause the video now and verify that for yourself. All right. Now, what if we have a situation where we have remainders? So the remainder situation I have dealt with here. When dealing with remainders, so whatever number you want to encode, you're going to reduce it by 60, which means you're going to subtract 60 from it. Then you're going to divide by 5. So if you get a remainder, then there are various things that you can do. Since you're dividing by 5, you can only have a remainder of 1, 2, 3, or 4. So if you have a remainder of 1, then you increase the values by 1 from the 21st cell on. If you have a remainder of 2, you increase by 1 all of the values from the 16th cell on. When I say the 16th cell on or the 21st cell on, that includes the 16th cell. So if, for example, in the 16th cell, you normally would have had a value of, say, 35, you will instead put 36. And then in the 17th, it would be 37, and so on until you finish. And of course, there are 25 cells in a 5 by 5. If you have a remainder of 3, then you increase by 1 in the 11th cell. And if you have a remainder of 4, you increase by 1 in the 6th cell. Now, let's do some examples. So if we have the divine name Al-Hasib, what do we do? Well, I'm not going to go... I didn't write out all of the abjad details here, but if you want to know, Ha is 8, Sin is 60, Ya is 10. It's not a very nicely made Ya. And Ba is 2. So 60 plus 10 is 70. 8 plus 2 is 10. So the number is 80. You reduce by 60, which means you subtract 60 from 80. You get 20. 20 divided by 5 is 4. So there is no remainder. No remainder. Since there's no remainder, it's just a straightaway filling up of the square. So you keep the original 5 by 5, or you memorize it, or you have some picture of it in front of you, and you fill accordingly, which means the minimum value will be 4, and you will put the 4 in the 1 position. So you'll have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. So let me show you how I did that. So here we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, then you will have 26, 27, and 28. So again, I would advise you to pause the video here, focus on this, and verify that every horizontal row, vertical column, and diagonal add up to the value of 80. All right, let's move to the next example. The next example is of the divine name Allah. We've done this one many, many times. Alif is 1. You've got 2 lams. So lam and lam is 30 and 30. That's 61. Plus ha, which is 5, is 66. Now, some people ask me, okay, so you have a shadda on the second lam. There's a shadda on the second lam. Does not mean you need to have another lam. The answer is no. That's not the convention or the rule according to which abjad values are calculated. So the divine name Lafzul Jalala, Allah, is 66. And so you see we have to subtract 60. That's an easy subtraction. 60 from 66 leaves us 6. Then we divide 6 by 5. Obviously it only goes in once, and so we have a remainder of 1, which means that we increase all the values by 1 in the 21st cell on. So again, our minimum value will be 1. So it's like the normal conventional square we learned. So we have our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and oh, it's into the 21st. So, okay, yeah, sorry. So 11, then you have 12, 13, 14, 15, 16, 17, 18, 19. We're coming up on it. You go to 20, and here would have been 21. So I've put that in green, and I've circled it. And then you can follow up the rest. So you have 22, 23, 24, 25, 26, filling up the rest of the square. Now, here as well, I would ask you to pause the video, verify that each horizontal row, vertical column, and diagonal indeed adds up to 66. So you pause the video now and check that for yourself. All right, you've unpaused the video. I want you to notice something. Here we had a remainder of 1. Because we have a remainder of 1, that means that in every sum, which is across or down or diagonal, we've got to have one number that's been increased by 1. And you notice that here in this row we have this number. In this row we have 22. In row 1 it was 26. In the third row going down is 23. In the fourth is 24 and 25. And you see also in each column you have one. And then in the diagonal as well, you see you have 7, 22, 15, 4, and 18. So that's the value in the diagonal that's increased by 1. And in 1, 8, 15, 17, 25 is the value increased by 1. And you will see that these remedies, so when we do our next example, when we increase by 1 in the 16th cell, that'll end up giving us 2 numbers in each row and column and diagonal that have been increased. And then when we do the next one, we'll have 3. And in the last one, you'll actually have 4. All 4 in each row and column and diagonal will have been increased, and there will only be 1 which will not have been increased. So we just did Al-Hasib, Allah. Now we'll do, we actually have to do 3 more examples if I show you one of each kind. I did one with 0 remainder, which was Hasib. This is with remainder 1. So now we need to do remainder 2 and a remainder 3 and a remainder 4, which I think I've got here. Yes, I do. Let us do this next. So for this, I chose Ar-Raqib. Raqib, and as I've said many times, you drop the alif and lam. And so Ra is 200, Qaf is 100, so 200 plus 100 is 300. Ya is 10, that's 310. Ba is 2, that's 312. 312 minus 60 is 252. If you divide 252 by 5, you'll get, it divides 50. 50 divides 252. So 50 is the quotient, excuse me. And the remainder will be 2. Since we have a remainder of 2, remember the rule is to increase by 1 in the 16th cell. So again, you're going to have 50, 51, 52, and you work all the way through. And then I will leave that to you to work that out. You will see that in each horizontal row, column, and diagonal, we have 2 values which are in green and circled in red that have been increased by 1. And so you see that the situation is remedied. And indeed, everything adds up to 252 vertically, horizontally, and diagonally. So here again, pause the video and study this square. Check that the sums are correct. They should be. If I've made a mistake, that's fine. Be happy to be corrected. Make it clear in the comments. So pause the video and check. All right, if you've unpaused the video now, we have our next example, which is of the divine name As-Sabur. You drop the alif and lam, so we have Sad, Ba, Waw, and Ra. And yeah, so Ra is 200, Sad is 90, so that's 290. Waw is 6, and Ba is 2, so it's 298. Okay? Subtract 60 from 298, you get 238. 238 divided by 5 yields a quotient of 47, which gives us a remainder of 3. With a remainder of 3, we must increase by 1 in the 11th cell onwards. When you do that, you will see that you will have 3 values, because if the remainder is 3, you need to increase by, you have it, increase by 3 in each row, column, and diagonal. And so here we have 3 numbers, 1, 2, 3, 3, 3, 3. Same for the diagonals. So I want you to verify all of that, in addition to that the sum vertically, horizontally, and diagonally gives you 298. So pause the video and please check that. All right, now that you've unpaused the video, we move to the final example, which is the divine name Latif, Al-Latif. We dropped alif and lam. We're left with lam, ta, ya, and fa. And yeah, so lam is 30, ta is 9, ya is 10. So we have 39, 49, and fa is 80. Okay, so that gives us 129. And then we subtract from 129, we subtract 60. That leaves 69. Then we take 69 divided by 5, we get a quotient of 3 with, this got a little smudged here. It's a remainder of 4. Obviously, that's going to be our last example. So we must increase by 1 in the 6th cell. And our minimum is 13, so we start with 13. And so when you do this, you notice that almost all of the numbers have been increased by 1. And the ones that aren't are blocked out here in dark blue, 13, 14, 15, and 17. Because we increase by 1 in the 6th cell. Oh, there was a 16. So in other words, you'd go 13, 14, 15, 16, 17, 1, 2, 3, 4, 5. So this would be the 6th cell, but it's 19, and it goes on from there. Okay, so here again, you should verify that all of the rows, columns, and diagonals give you a value of 129, and also be sure and convince yourself of this rule for the remainder. So you can pause the video and do that, but the video basically concludes here. So this is our 5x5 all set out on these pages. To summarize, I only know of this one form of the 5x5 as it's configured here, starting from the corner and going with the knight's move, 1, 2, 3, and then onwards. It's important that you learn this formula if you really want to work on magic squares and play with, experiment with them. If you know this, you will be in a good shape. And then, of course, there are the rules for the remainders. We've covered that in the case of the 3x3 and the 4x4 as well. And then I went through these examples. So given the sophistication of the 5x5 and how it's very easy to make mistakes, I sort of shortened this video and wrote everything out before. And so I think maybe you need to watch the video couple of times, 2 or 3 times, and get some graph paper and make these squares and work them out for yourself. And then afterwards you can experiment and come up with any value you want and play around with these. And there's really some very sophisticated mathematics here. So I think this video will allow you then to experiment with the 5x5, and we've done the 3x3 and the 4x4. And I welcome your questions and comments. Please keep those coming. And I am thinking about making more videos about even higher order magic squares, but they get pretty complicated. And it's very easy to make a mistake when you construct them, even with the 5x5, because with the 3x3, it's easy. You can tell where you are, because there's only 3 rows and columns. You know you're in the middle. And same with the 4x4, you can orient yourself. But after a while, you've got these larger and larger grids, and it's easy to get lost. So I might do another one on the 6x6 and, move on up to maybe 12. And then maybe talk about some higher order squares, and maybe even make a video on the 100 by 100 in the coming, weeks and months. We'll see how it goes. If you are interested in those higher order squares and the mathematics of those squares, and then do let me know, and I'll possibly make more videos along the lines and format of this one. All right, that's pretty much it for this video. Thank you very much for watching.